Hi, welcome to this subject of advanced engineering mathematics. So we are in this module, first order ordinary differential equations. In this lesson, we'll talk about some of the basic concepts on first order ordinary differential equations and some modeling. Many physical laws and relations can be expressed mathematically in the form of differential equations. Thus, it is natural that our module opens with the study of differential equations and their solutions. Indeed, many engineering problems appear as differential equations. Module number one, or in this first module, our study begins with the study of ordinary differential equations, or ODEs, by deriving them from physical or other problems, solving them by standard mathematical methods, and interpreting solutions and their graphs in terms of the given problem. The simplest ODEs to be discussed are the ODEs of the first order, because they involve only the first derivative of the unknown function and no higher derivatives. If we want to solve an engineering problem, which is usually of a physical nature, we first have to formulate the problem as a mathematical expression in terms of variables, functions, and equations. Such an expression is known as a mathematical model. The process of setting up a model, solving it mathematically, and interpreting the result in physical or other terms is called mathematical modeling, or briefly modeling. Modeling needs experience, which we shall gain by discussing various examples of the problem. Now, many physical concepts such as velocity and acceleration are derivatives. Hence, a model is very often an equation containing derivatives of an unknown function. Such model, such model is called a differential equations. A differential equation. We then want to find a solution for that particular equation, explore its properties. We would want to graph it, find the values of it, and interpret in physical terms. Uh, so that we can understand the behavior of that particular systems in our given problem. However, before we can turn to methods of solution, we must first define some basic concepts need, needed throughout this module or chapter or lesson. To begin, let's define an ordinary differential equation. Okay? An ordinary differential equation, or ODE, is an equation that contains one or several derivatives of an unknown function. An ODE is said to be of order n if the nth derivative of the function y is the highest derivative of y in the equation. So, in this lesson, or actually throughout our discussion of first order ODEs, we shall consider two forms of expressing a differential equation. So first, we have this implicit form, such as a function on the left side of an equation, of the equation, function of x, y, and y prime, for example, is equal to 0. So we call this a form when the equation is written as an in the implicit form of equation. We also have the other one, or more oftenly used form is what we call the explicit form. Okay? So in contrast, implicit form, we have all our expressions or variables on the left side of the equation, while in the explicit form, we have variables and expressions on both sides of the equation. On the left side, usually we have this y prime and then function of x and y on the right side. Okay? So again, an ODE is said to be in the order n if the nth derivative of the equation or the unknown function y is the highest derivative of y in the equation. So I have listed these examples uh, in this table to illustrate the characteristics of differential equations. Okay, so first we have this equation y prime is equal to cosine x. So in this equation we have one variable. So this is indeed an ordinary differential equation of the first order, and it is written in the explicit form. Next, we have y double prime plus 9y is equal to e raised to the negative 2x. So this differential equation has one variable, and it is also an ordinary differential equation, but it is on of the second order. Okay? Because the highest derivative is the double prime or the second derivative of y. This equation is written in the explicit form. Next, we have y prime times y triple prime minus 3 halves y prime squared is equal to 0. Obviously, this equation is written in the implicit form. This is also an ordinary differential equation of the third order because the highest order is on the y triple prime. And lastly, we have this second partial derivative of u with respect to x plus the second partial derivative of u with respect to y is equal to 0. So in this case, we have two variables. Okay, this is a partial differential equation contrasting our ordinary differential equation defined, and it is in the second order written in the implicit form. Okay, I hope this helps you kind of visualize or characterize a certain equation using these examples. Okay, so concept of a solution. A function y is equal to h of x is called a solution of a given ODE. F of x, y, and y prime is equal to 0. On some open interval x greater than a but less than b, if y is equal to h of x, or the function, if the function is defined and differentiable throughout the interval and is such that the equation becomes an identity if y and y prime are replaced with h and h prime respectively. So uh, this is a straightforward definition of a solution. Okay? But then let's illustrate or further explain what a solution or the concept of a solution is with this particular example. So let's verify a solution. Verify that y is equal to c over x is a solution of the ordinary differential equation x y prime is equal to negative y for all values of x not equal to 0. And c is an arbitrary constant. Okay? So first, we have this given y is equal to c over x. So what we will do is that we will differentiate this equation. Okay? So we will have y prime is equal to negative c over x squared. Then we will multiply both sides by x. So the intention is that we are going to come up with an equation wherein we can see the given equation. Okay? So if we multiply this equation by x, the resulting equation will be x y prime is equal to negative c over x. So this red font here, okay, is actually our given. So if we replace this c over x with y, we will have x y prime is equal to negative y. And this verifies the solution y is equal to c over x is a solution for this particular ODE. Okay? Another example. So in application, we can use these two equations for exponential growth and exponential decay. So I'm just listing out some examples. No? Although we have references to other applications, but we don't have the time to present them here. So we have, for example, an equation representing an exponential growth. Y is equal to c e to the point 2 t. Okay, so that's an equation representing an exponential growth. Okay, so where c is an arbitrary constant. So if we differentiate this particular given, we will then have y prime is equal to 0.2 c e to the 0.2 t. If we can see here, we have c e to the zero point 0.2 t equal to y. So if we replace it by y, we will then have y prime is equal to 0.2y as our differential equation. Okay, so therefore we can say that y is equal to c e to the zero point 0.2t is a solution to the differential equation y prime is equal to 0.2y. If we graph or plot the points of these solutions to y prime is equal to 0.2y, we will be having what we call as a families of curves. Okay, so since c is an arbitrary constant, if we replace c with different values, therefore we will have different curves on the graph. So the solutions for y prime is equal to 0.2y is these lines. And uh, on the other hand, if we have the exponent of this given to be negative, we call that the exponential decay. Okay, so solving that equation with the same approach will give us this particular families of curves. Okay, so we go now to the concept of initial value problem. So in most cases, the unique solution of a given problem uh, is obtained from a general solution. Okay? So again, in most cases, the unique solution for a given problem is obtained from a general solution through or using an initial condition. Okay? So, uh, in this case, we have a particular initial value that we will use to get a unique solution on a particular differential equations. So, this unique solution is what we call as particular solution. Okay? So in the previous examples, we can see that we have this value of c, which is an arbitrary constant. So to get the particular solution, we we want to eliminate or identify this value of c so that we have an equation that doesn't have a variable representing a arbitrary constant. Okay? So geometrically, this condition means that the solution curve should pass through the points given in the initial value uh, so that it is unique. So an ODE together with an initial value is called an initial value problem. So to represent this statement with equations, so we have y, for example, y prime is equal to a function of x and y with initial condition y of x sub o is equal to y sub o. Okay, where x sub o and y sub o are our initial values for this particular uh, problem. So to further illustrate or explain, let's solve this example. We would like to find the general solution and particular solution for y prime is equal to dy dx is equal to 3y with initial condition y of 0 is equal to 5.7. So again, we have this uh, differential equation dy dx is equal to 3y. So to solve this equation, what we will do is to manipulate and then uh, move y to the denominator of dy while dx on the right side of the equation so that we have this particular setup. We have dy over y is equal to 3 dx. Okay, so next step is to integrate this equation. Okay, so if we are going to integrate this equation, we will have this uh, result. So the integral of dy over y is the logarithm of y, and it is equal to the integral of dx that will be um, 3x plus c. Do not forget the c after doing the integration, right? So therefore, if we are going to simplify this equation, we will come up with y is equal to c e to the 3x. Okay? So we call this the general solution because we still have the arbitrary constant in this equation. And to get the particular solution for this y is equal to c e to the 3x, we will have to use our initial values here. Y of 0 or y of 0 is equal to 5.7. So what we will do is to substitute the values of x and y to get the value of c. So, so y is equal to c e to the 3x. Substituting the values of the initial condition, we have y of 0 is equal to c e to the 3 times 0 because our x will be 0. And we know that y of 0 is equal to 5.7. Therefore, we have 5.7 is equal to c. The e was eliminated because anything raised to 0 will be equal to 1. So therefore, we have c is equal to 5.7. We then go back to our general equation and substitute our c, or the constant, to get our particular solution. And that will be y is equal to 5.7 e to the 3x. Okay, so that's an example of uh, an initial value problem. Okay, so to summarize, we defined modeling, and we defined unordinary differential equations. We also characterized these different examples of ordinary differential equations, and we solved basic problems to illustrate the concept of a solution. Then uh, we showed an application of getting the solution of a particular differential equations. And lastly, we introduced the concept of initial value problem. Okay. For the rest of for the succeeding lessons, we will use this concept on initial value problems more often. Okay. So uh, and then on the succeeding lessons, we will learn uh, different methods in solving different types of ordinary differential equations. Okay, so this is the end of the lesson. Thank you.